Okay. For you guys, for the 8 o'clock class, I think the web is updated except for the quiz from Friday, which if you missed, you have until 5 o'clock today to take. And then I will update, then I'll put the answer key for that on. I think the 9 o'clock class, I still have to update the grade book, but you guys are okay with yours. So for the exam on Friday, it goes up through the end of chapter 18, I believe. Amines are not on the exam. So there's no naming of amines. Amines will be on the next test, which isn't that far away, right? I think it's in a couple of weeks. So
does it go to?
It goes to the end of, so it goes to what? Friday? The Friday before last Monday? Because Monday, well, it goes till Monday. Part of Monday was on ketones and aldehydes, and then part of it was on the amines. The amines part will not be on, won't be on the exam. So, and what I'm going to talk about today won't be on the exam, but I do have, there is some review here of stuff that will be for Friday. Tomorrow we'll use tomorrow as a review session. So if you got questions on any of the electrophilic aromatic substitutions, and really all of the electrophilic aromatic substitutions are going to be fair game for tomorrow because you'll need all of them if I give you problems, and I will, going from benzene to some other molecule. So it's, and also to react mono and multiply substituted rings. So the only thing that wouldn't be part of electrophilic aromatic substitution is the mechanism. I wouldn't ask you to write the mechanism of electrophilic aromatic substitution. But as far as the mechanisms go, you want number on. Okay.
What mechanism did you say you needed to know?
The list of mechanisms, nucleophilic aromatic substitution, the imines, hydrates, enamines, acetals, hemiacetals, all the ones that I put on the homeworks that I put online before. I tried to put all the ones that would be relevant, including the reverse mechanisms that if you ended up with a hydrate, I could ask you to go in reverse from the hydrate to the ketone or aldehyde. So both forwards and backwards. So if you take a look at those, that would be your list. I know I'm going to have to come up with a list for somebody in the next few days, but that's, if you go through the homework where there's mechanisms, those are going to be the ones I would ask. That's the quickest place to look, or your notes. Okay, for amines then, and there will be some electrophilic aromatic substitution and some review questions here. So in terms of the amines, we've kind of talked a little bit about naming amines, and before the next test, I'll actually go to whatever color book it is on the IUPAC website and pull up the exact rules for naming amines, because the book is a little confusing in terms of what terminology they use. And I've tried to be, with the homework problems that I put on before break, I tried to be consistent with that. But that's not, to be honest, that's not going to be something you're going to be looking at before Friday, right? But in terms of amines, we're next at sort of the physical properties of amines. And so the biggest physical property of amines that are going to be an issue are that if you have an amine, they can both form hydrogen bonds to themselves as well as hydrogen bonds to alcohols or waters. They can both donate. For instance, if I took amine and dissolved it in water, I could form a hydrogen bond from the NH to the water, and the nitrogen could also then accept the hydrogen bond from the water as well. And so for, physical properties of amines, their strongest intermolecular force within themselves is going to be hydrogen bonding. But the amines, because the nitrogen isn't as electronegative as oxygen, amines don't hydrogen bond within themselves nearly as strongly as oxygen, as alcohols do. So if you were to compare boiling points of amines to alcohols, the boiling point of amine would be a little bit less, with comparable molecular weight and with comparable size of the R group. But amines tend to be really water soluble as long as this R group is small. Once the R group gets larger or becomes aromatic, then the amine is not as water soluble. So it's kind of similar physical properties as to what alcohols have. Now, there is a difference in terms of acid-base chemistry of amines that I'll talk about in a minute, and that's going to play a large role. There are a couple of amines that, amines have a fishy smell. Part of the reason they have a fishy smell is because fish waste is amine, is nitrogen-based. And also when fish rot, they make two compounds. There's actually butane 1,4-diamine, which would have the NH2, and then it would have the 4 carbons here, and then another NH2. So butane 1,4-diamine is also called putrescine, which I think the name pretty much tells you what that is. And then if you add an extra carbon to that, you end up with another product that's called cadaverine. And so those two are examples of basically why amines have this fishy smell, because when fish die, or when they start to decompose, they form those compounds. And they both have relatively obnoxious smells. There are people that try and sort of age the freshness of fish by seeing how much putrescine and cadaverine are in the fish to make sure it's fresh and not overly decomposed. Probably they don't have a portable instrument at the grocery store to check that, but it is one way to do it. Usually they don't use a GCMS, they use something a little simpler, one's nose. But that's why you end up with that amine. An amine is typically a fishy smell because of where they come from. So amines, pretty similar to alcohols in terms of water solubility, boiling points, etc. Of course, you can take this amine. This is an N with 2 H's, so this is a primary amine. As you go on up the scale, so if you make a secondary amine, there's less opportunity for hydrogen bonding. And if you went to a tertiary amine, which has 3 R groups, all the nitrogen can do is accept the hydrogen bond. It can't form a hydrogen bond or donate a hydrogen bond. So it's going to depend on the particular amine. And the putrescine and cadaverine, and there are some other ones. There's a 2-carbon amine that's called ethylene diamine. They tend to be really water soluble because there's 2 nitrogens. And so they're very difficult. Once they get into water, they're really difficult to get out. So when we're synthesizing amines, they can be exceptionally difficult to actually extract from water. Okay, so amine basicity then. You know from general chemistry that NH3 would react with water, and there'd be an equilibrium between the NH4 plus, the ammonium, and the hydroxide. So we would consider ammonia to be a base because it produces hydroxide. It would be both an Arrhenius base, because that's the definition of an Arrhenius base, is something that produces hydroxide. And we could figure out what its pKb is, or look it up on a table, and if this was general chem, we can make ice charts and everything else, but we're not going to do that. The only difference between ammonia and a primary amine is just simply adding an alkyl group. So you're going to have these similar properties, meaning that the nitrogen could pick up a proton and then become now an ammonium, what we call an ammonium salt. And that's the term we would use, would be an ammonium salt. This would be sort of an alkyl ammonium salt. You could end up with a dialkyl or a trialkyl ammonium salt, depending on how many R groups you start with. But basically, nitrogen can accept a proton. And that changes the nitrogen from being a nucleophile. It would change it to become an electrophile, except the problem is nitrogen can't form an expanded octet, so there's no way I can bond something to that nitrogen. So we have to be careful when we're doing the reactions of taking, let's say, a ketone and reacting that with, let's say, a primary amine. One of the things we didn't do was we didn't add acid to this mixture because, number one, nitrogen doesn't need it because it's to the left of oxygen. It's a more powerful nucleophile, so it can directly attack the carbonyl. But number two, if I added acid, then it would protonate this, and that would no longer be a nucleophile. So when we did this reaction with alcohols or water to form acetals, hydrates, ketals, etc., we needed acid as a catalyst. We don't use it here because if it's there, then you don't get a reaction, because all that does is protonate the nitrogen, and then it can't act as a nucleophile anymore. So that's why we didn't see nitrogen have an acid with it. So in terms of, the basicity, then, there is the ability of the nitrogen to accept a proton. We could deprotonate the nitrogen to make an N-, but we'll need a Grignard or an H- in order to do that, right? Because nitrogen N- is towards the end of our strong bases. So a nitrogen group could go either way. We've used N- as strong bases. Now we're going to use the nitrogen as a nucleophile, like we started, like we did here, and that like we will do more. We're going to start adding alkyl groups to that and use the nitrogen as a full-blown nucleophile. But we can't have acid present if we're going to use it as a nucleophile, because that will keep nitrogen from acting as a nucleophile. All right. In terms of base properties, then, here's the trend. The trend is that secondary amines are stronger bases than primary amines, which are stronger bases than tertiary amines. Now, why doesn't it go primary, secondary, tertiary? Why doesn't it go tertiary, secondary, primary? Well, because it has issues. Here's what I'm looking at in terms of that acid-base equilibrium. And I'm going to put an H here. And I'm just going to leave I'm just going to use the most generic structure I can. So there's our equilibrium between the base nitrogen and the acid ammonium. What would stabilize the product? Let's go back to one of the basic principles, hopefully, that you remember. Hopefully you take more than this away from the class. But one of the ways to shift the equilibrium towards the product is to do what? Make the product more stable, right? So if I want to make a stronger base, if I want to make the nitrogen a stronger base, and shift the equilibrium towards the right, what can I do to make the product more stable? Make it more substituted. So what happens with the carbon? The carbon, the hydrogen becomes delta plus, the carbon becomes delta minus, and an alkyl group can stabilize the N plus charge by donating electron density. If you're sitting there shocked by that, where have you been the entire year? Because how many times have we done this in the past? Radicals, carbocations, double bonds, right? This is our explanation for carbocation stability, radical stability, why more substituted double bonds are more stable. So one of the ways to make a stronger base is to add more alkyl groups. But that doesn't work here, right? Because if that was the case, then what would be my trend? My trend would be tertiary is the strongest base, then secondary next strongest, and primary least strongest. So that is a factor. Okay, so number of alkyl groups here is a factor. But then there's also another factor. And that factor is that when we measure basicity, we measure the basicity in water. So if you have a primary ammonium versus a secondary ammonium versus a tertiary ammonium, solvation works against the tertiary ammonium salt. Because not only is it that you can push the equilibrium to the right by putting more alkyl groups on this nitrogen and pushing electron density into it, but I could also stabilize this product by being able to solvate it with water. And so what happens is that with a primary amine, you have only one alkyl group stabilizing the plus charge, but you have the most solvation of water. Well, the problem is that not only does the water solvate the product, it also comes over here and it also solvates the reactant. So it's kind of it solvates the reactant more than it solvates the product. And when you go to a secondary, it turns out that the secondary, they kind of cancel each other out a little bit in terms of sterics and then the stability. So it turns out that this solvation for primary is more than this solvation over here. So primary gets moved to the second position. Secondary, more alkyl groups to stabilize the plus charge, and then solvation's kind of a wash in both cases. So it gets the pure alkyl group donation. And then when you go to tertiary, the problem with a tertiary is you got 3 alkyl groups, so you don't get much solvation of water. So there's 2 factors that kind of come into play, and in the end, you just have to remember that the secondary, that it goes secondary is the most basic, followed by primary, and then tertiary. Tertiary amines one would think would be the most basic, and they're not. They're the least basic. Okay. So there is these 2 factors that kind of play off against each other. But what we know experimentally is secondary is the most stable, or it basically pushes the equilibrium the most, because the hydrogen bonding in these 2 cases cancel, So it gets the full effect of two alkyl groups. In the tertiary case, we have hydrogen bonding really kind of affecting. It counterbalances and actually pushes the equilibrium more to the left. I know it's kind of confusing, but does that kind of make sense? There's just two factors that are kind of opposing each other here. So how about other amines with amines, basicity-wise? Alkylamines tend to be more basic than arylamines. So when you do have just R groups attached to your nitrogen, those are stronger bases than having a benzene ring attached to a nitrogen. And the reason for that is that if you take your aromatic, now your NH2 group is attached to the aromatic ring. I'll talk about what happens when it's inside the aromatic ring in a minute. But if I was to take that and I was to write it out how it would normally look, here's what happens. The nitrogen's lone pair now gets extended into the conjugated system here of the benzene ring. So we know the benzene ring, all these pi or all these p orbitals are conjugated. It's an endless electron density. But what happens is that the nitrogen there also is involved in that conjugated system, and so the NH2 or the NH or NHR or the NR2 groups, anyway, the lone pair on the nitrogen, then becomes parallel to the other p orbitals in the ring, and it gets caught up in the extended system. Now, what does that do to the equilibrium then? What that does to the equilibrium is, remember that the equilibrium is the NH2 plus H plus is in equilibrium with the NH3 plus, and what happens is that stabilizes the reactant. So this lone pair becoming part of the conjugated system stabilizes the reactant. And which way does the equilibrium shift? To the left. So if the initial reactant is stabilized because that lone pair, then it shifts the equilibrium back to the left, and that makes it a weaker base. We don't have that issue with the non-aromatic amines. There's no conjugation that's possible, and so in general, aryl amines are less basic than alkyl ones. And then the other trend that happens is sp2, sp3, and sp. So an sp3 hybridized nitrogen has the nitrogen, the lone pair, more accessible than an sp2 hybridized nitrogen, and that's more basic than an sp. So if you had a nitrile, a C triple bond N, this lone pair, because it's sp, it's in an sp hybrid orbital, it's less likely to take on a proton than if the nitrogen is sp2. So this is the weakest, and then this is weaker. And then, of course, if you just have a nitrogen that's sp3 base, that's the strongest in that set. So it has to do with the availability and the sort of the S character of where the lone pair is. So in sp3, the lone pair that's in an sp3 orbital is going to be more likely to take on a proton than sp2 or sp. So those are the empirical trends that we find. And A lot of that just has to do with the positive charge in terms of putting the positive charge. Putting the positive charge on an sp nitrogen is not good. Putting a positive charge on an sp2 nitrogen is not good. We have talked about the fact that an sp2 hybridized carbon, meaning a carbon that's attached to a double bond, does not form a carbocation. And the same thing would be true for the nitrogen there. So other than just flat out learning it or memorizing it, you'd have, if you remember that the carbon with a double bond doesn't like a positive charge and nitrogen with a double bond doesn't like a positive charge. Neither does it, and a nitrogen with a triple bond likes it even less. Okay. So those are kind of our trends for the physical properties. I think there's one more. The one more we've talked about. So we put the nitrogen inside of an aromatic system. We make a heterocycle. We've already talked about these rules, right? So my question is, for the first one, for the pyrrole, aromatic, yes or no? What do we think? So I push it, it's not going? Okay, let's stop it, let's try it again. 2 answers. Now try it.
What was the question?
Hold on. Okay. The question is this aromatic? I'm sorry, no, that's not the question. The question is that nitrogen basic? Is the nitrogen inside of the pyrrole ring basic, yes or no? Will that nitrogen accept an H+? So that's the question. Does aromaticity have something to do with that? Yes. But is this nitrogen basic? Yes or no? Okay, got a couple people left. Everybody's got a clicker, because I do have more questions, because I know everybody's bored, because we don't do this anymore. And trust me, I can see it. Everybody answered? Did I count wrong? 15, 18, 21, 22. 2 people not voting. Do I need to find out who they are? Because I can do that. Last person. Take a guess. Too late. 62% say that nitrogen is not basic, 38% it is basic. Okay. For the second one, is that nitrogen basic? A for yes, B for no. So in purity, is that nitrogen basic, yes or no? Thank you. 73% yes, 27% no. Not 100, but that's okay. It's still 8 in the morning, a day after break. What am I looking for in terms of nitrogen being basic? What needs to happen? The lone pairs need to be available for the H plus to bond to it. Are they available in this case? Yes. Why?
Because it's not part of the aromatic system.
Because it's not part of the aromatic system. Now, is this lone pair over here on this nitrogen part of the lone? Is that part of the aromatic system?
Yes.
Yes. Because in order for this pyrrole ring to be aromatic, it needs to have all of the atoms sp2. Well, nitrogen can adopt sp2, and when it does, what happens to this lone pair? It goes into the p orbital, and then I have 2 plus 4 plus 6. Once that lone pair is required to make the system aromatic, H plus can no longer bond to it. So, A, is that nitrogen basic? No. Is this nitrogen basic? Yes. Okay. So we have to remember that. From, I don't know how many weeks ago it was. It seemed like it was 3 months ago. It wasn't that long ago, but we need to remember that for the amines, for heterocycles. Okay, so basicity, aliphatic, non-aromatic amines, it goes secondary, primary, tertiary in terms of strength of amines. In terms of aromatic, an NH, an N group that's attached to an aromatic ring, less basic than one attached to a non-aromatic ring. And then hybridization, a nitrogen that's attached, or a nitrogen that's sp3, most basic, sp, least basic. Those are the trends that you have to remember along with this. All right. So, now, I don't know why they don't talk about the synthesis of amines. I guess we will. They jump right into review. Oh, look, a review for Friday. So, for these two reactions, I've given you 3 possible products. So there's 3 answers. So for reaction A, what is the major product of reaction A? Is it molecule A, B, or C? And then for reaction 2, I'm going to give you the same ones. But let's do A first, or number 1 first. Reaction number 1, what's the major product? And is this relevant for Friday? Absolutely. What do we think? Last 2 people. Last person. Okay. What are the answers? Answers. 82% say A. Not bad. What kind of amine is this? It's primary. So what does it form? A Schiff base. Or an imine, which is A. So A is the correct answer. C is what? C is one of the products along the way towards the final product. So this, and I forget, the book uses a strange term for this because this is called an aminal. Actually, it's an aminal. It's still an aminal, whether it's a ketone or not. But that's a compound along the way. But the final product is A. Good. So now we say for B, what's the final product then? For reaction 2, what's the final product? A, B, or C? Bless you. %, say B. Well, that's good, except I should have put D down, none of the above. Because what's the problem with B? The problem with B is this nitrogen should have what? An R and an R prime. Okay, but of your choices, leaving it blank would have been the most correct one, but that's okay. Apparently I can't use the same set for those. Secondaries form enamines. Okay, so that's one of the reactions of amines, review reactions. Let's see, do we have more review reactions? Why we do? This one I have 5, 6, 7 possible answers. So if I was to react NN-dimethyl-aniline with chlorine and FeCl3, what product or products would I get? A only, B only, C only, then D, A and B, A and C, B and C, or A, B and C all together. What's the major product of this reaction? Is this relevant for Friday? Yes. See, it's a little mini review day, too. Okay, what did we say? Whoa. 91% answer E, which was A and C. So the nitrogen is a orthopara-director. It's activating. Did anybody put C only? No. Probably would have taken C too, because you could, if you were going to answer C, you could make an argument that this is a big group and it's sort of blocking the ortho position. But ortho and para is correct. Good, we remember that, or 91% of us remember that. Now, here's a new reaction that I didn't talk about. But take a minute. What would be the major product of this reaction? So now I'm going to nitrate the heterocycle. Where's the NO2 going to go? Is it going to go to A, to B, to form C, and then the other mixtures? Okay? And if you're sitting there going, we didn't learn this, you're correct, we didn't. So take 2 minutes and think about what's going to happen when you add the NO2 plus to the ring. product of this reaction is. We should have saved this for Friday, because that would have been fair game. Sure would have been. Where's the NO2 going to go? Where's my clock? Where do you think it adds? Think back as to how we showed, and this goes back to before spring break, but how did we write the mechanism of the addition of an electrophile to a substituted ring so that we knew that orthoparadirectors were indeed orthoparadirectors, or a metadirector was a metadirector? Then worst case scenario, you could guess. Last 6 seconds. Okay, what did we get? So you got 36B, 36E, which is what? A and C. And then we got 14G, which is everything. And then we got a C. We got no A's. Okay. Well, what's the correct answer? That's a good question. When I add my electrophile to this ring, what would be the best position to have the positive charge? Where is the positive charge going to be the most stable?
At nitrogen?
On the nitrogen?
Yeah.
So in other words, add it here, and so we would have our H and our NO2 group here, and then we'd have our nitrogen there with the positive charge. Is that going to be the best? I mean, how many resonance structures can I draw off of that? If that's what happens. If I add the NO2 group here, let me clean this up a little bit. But if I add the NO2 group there, if I add the NO2 group here and put the plus charge on the nitrogen, how many more resonance structures can I draw off of that?
2.
Can I draw any more? Right, because what would I want to do? Well, I suppose I could bring this pair of electrons down here, right? And then I could bring this pair of electrons over there. So I would get like 3.
2.
That's not bad. So 2 more. So I could get 2 more resonance structures off of that. So that one plus 2. What if I added the electrophile to this position? What would I get? How many resonance structures could I draw there?
No.
Well, let's see, could I do this? And then form that. But then what do I do? Then I'd have to do this, right? And then I could do that. So if I put the NO2 there, how many more did I get?
2 more.
Well, I got 1, 2, and then there's a third one here. So I got this one, I would get that resonance structure plus 3 more. So, based on number of resonance structures, where would the NO2 go? Is it going to go here? Or is it going to go here? What? Meta to the nitrogen. Based on the number of resonance structures, it would go meta to the nitrogen. If you buy that this is legitimate. Right? I mean, does that look legitimate? It's a little rough, I would say, based on that structure. What's wrong with this? What issues does it have?
Sterics.
Not so much sterics. If I asked you in this case, what's the hybridization of that nitrogen? We got 3 choices, sp, sp2, sp3. What'd I hear? What? SP. What's the usual bond angle for an SP? 180. Is that 180? Can it be 180 ever? Not in a 6-membered ring. But I seem to remember that guy being formed as an intermediate in a reaction. And what would the hybridization of those two carbons in the triple bond be? SP, are they 180 degrees? Hell no. They're not even close. So, if this is legit, and it is, and it's a mechanism that could show up on Friday, then this has to be legit. And so, where it actually adds is it actually adds to this position, because we can end up with an additional resonance structure. All right, not the most stable resonance structure of all, but still an additional resonance structure. Ultimately, here's what we choose, what we base our choice on, what the reaction does. So if we take purity and we add NO2 to it, we get product B as our product. And our rationalization for that is that we can get an additional resonance structure if I add to B that I can't get from A or C. And so in that case, we always nitrate meta to the heteroatom, because the intermediate puts a positive charge next to the nitrogen, and next to the nitrogen we get that additional resonance structure. Okay, at least that's what I remember seeing in the book. Hopefully I didn't do it wrong, but that's what we get. Okay, so tomorrow then, no in-class quiz. Review, bring your questions. If you have questions, email me or stop by and see me. The quicker you get your questions answered, the better off you'll be. So you don't have to wait till tomorrow, but bring them. Otherwise, again, we'll stare awkwardly at each other. But I do have additional stuff that I can go over tomorrow if that's going to be the case.